This has been truly one of the most fun hours. So I really thank you for your time. It was super enlightening. I learned a ton about like physics, history, the future. The whole thing. Yeah, I'm a new man walking out of this conversation. Hey, I'm Nader from NVIDIA.
I'm Stephen from NVIDIA.
And I'm Carter from NVIDIA.
One of my favorite things about working here is that we get to meet incredible minds like Stephen and actually just sit down and have a conversation. I think we're going to call this video series NVIDIA is a software company, because that's more or less what it is.
Yeah, I mean, we have more software engineers than hardware engineers, right?
Yeah.
I remember actually Jensen, like several years ago, was like, this is not a hardware company anymore, this is a software company now.
Yeah, well, that makes sense. I think a lot of people hear about CUDA, about how much of it is a moat, how useful it's been for developers. You're on the CUDA team?
Yeah, I'm one of the CUDA architects. So
Okay.
I've actually been on CUDA since 2008.
Okay.
So I joined when it was 12 people. And here's a funny story. I joined, and it was totally new. This random little startup inside NVIDIA for using the GPU, which was totally graphics at the time, to do compute. And I get to NVIDIA, and everyone's mad at us. And I'm like, what's going on? Because I had no idea. And it turns out, like at the time, the most important thing was 3D mark, right? How fast you could get 3D mark, because that's the graphics benchmark, right? And so Jensen had said, 10% of the chip is going to this CUDA thing. It's going to this programmable stuff. And all the graphics guys are like, that's 10% less 3D mark. And they're super pissed off about it. And I had no idea I was coming into the middle of this, right? and the irony is that now it's like, even the graphics is 90% programmable and 10% fixed function hardware.
Funny.
So it's literally flipped around anyway. All the stuff we did for CUDA turned out to be totally useful for games and all the rest of it.
Yeah, amazing.
I have a question, which is, what was the GPU before CUDA? How would people interface with it, and what role did it play in this?
Like how would game developers interface with it?
Well, just in general, like I think that a lot of people, CUDA has become so synonymous with the GPU, and obviously and particularly NVIDIA GPUs. But how did people work with GPUs before CUDA?
So there were things like OpenGL and DirectX, which had come up in like 2000-ish. I can't remember the exact date. And I'm not a graphics guy, but you'd set up your scene of your 3D objects and your and you'd render it. And OpenGL was kind of a language for like structuring these things and matrix rotations and so on. And then OpenGL started to add a few programmable little script bits. So you could have, morphing your geometry and things. And that little bit of programmability, they call it programmable shaders, is the thing that was the genesis of having not fixed function hardware on the GPU, but a little bit of programmable stuff. So it was like texture mappers and rasterizers, and then a little bit of this programming stuff. And so some people, certainly at Stanford, Ian Buck, who was the inventor of CUDA, his PhD was a thing called Brook, and he figured out how to take a normal compiler and map it to some of this programmable stuff. He was an intern at NVIDIA. He somehow persuaded Jensen that this was worth 10% of the chip, which is why everyone was mad at us. And then the rest was history. But it actually coincided with the graphics people saying, hey, this dynamic, programmable, shading, geometry, all that kind of stuff, that makes better games, that makes better visual effects. And so the stuff that we built for graphics and the stuff that we built for compute started to look the same, right? It had functions and loops and variables and a C compiler. And so like the genesis started out as this fixed function rendering, and then to make the graphics better turned out to be the same thing as making CUDA.
So fixed function rendering means that you're compiling down to, well, you're not able to, there's no CUDA kernel. Can you explain fixed function rendering?
So originally, what you would do with something like OpenGL is you'd say, here's a sphere, here's a cylinder, here's like a pile of triangles, which is my surface or whatever, and you'd literally upload a mesh of your world to the hardware, and the hardware had these mechanisms for like crunching through triangles and putting them on the screen. I mean, that's really all the graphics card is a triangle generator. and so it was, what you started out doing was say, here is a list of triangles, and then here's the next list of triangles where they've moved slightly, and here's the next list, and so on. And the graphics driver, one of the interesting things actually in graphics is that more than half of the brains is in software before you reach the hardware. So the OpenGL driver, the DirectX driver is incredibly complicated. There's compilers built in and all sorts of things, because the hardware itself, its job is maximum triangles, maximum speed. And so all the brains and intelligence comes on the software layers and the drivers. And nowadays, of course, you have these shaders, these kernels, which manage and control the way your geometry deforms and moves. So the fixed function rendering was just, here's a triangle, here's a texture, put them on the screen, and here's a giant list of it, do lots of them. Mm-hmm. And that just evolved to, well, I want a bit more control, or I want to add some lighting, or I want to do these other things. And that just, then it became ultimately purely programmable, because there's no way that a fixed function machine can have all the things you can just arbitrarily write in software. Like, what if you want 2 lights or 3 lights? It's like,
so it's just like a nice abstraction layer higher for you to...
Yeah, exactly. It's more flexibility. It's harder because you can custom build transistors to really crank through the triangles. And the texture mapping hardware remains texture mapping hardware. There's a few things which are always going to be faster and more efficient in hardware, like rasterization. That's taking a triangle and lighting up a pixel on the screen. There's just no way you can do that in software as fast. But pretty much everything else, it turned out that we could make these very lightweight threads in the GPU, which could execute basic code. In the old days, you couldn't have I think you couldn't have a for loop. You had to unroll everything, you couldn't do functions. It was really, really super basic. But it was enough that you could take a few variables, add them together, have another variable, do a square root, that kind of stuff. And so a little bit of computation turned into a bit more control. And then there came a point, I don't even remember exactly when that point was, where we crossed over and we said, okay, let's put programmability in even if the graphics doesn't need it yet. And then the graphics started to catch up. I think that was about the Kepler architecture when we really started building compute-specific things. And so, now you see the complete opposite, where in many ways, the big advances you're seeing in graphics are coming from these really intelligent AI shaders, neural network shaders, like these machine learning
RTX chips?
Yeah, the RTX stuff. Ray tracing is yet a different technology, but just the RTX ability to embed little tiny machine learning algorithms, which can procedurally generate stuff, if you like, but much more sophisticated than a basic procedural generator. You get these people doing 3D textures of marble and things, so you can slice marble and the AI is just here's what it looks like. And it's way, way, way faster than you could do with a normal software algorithm. And so you're taking, that's the magic of these machine learning algorithms, right? Something that would be like a very long, complicated calculation can be done almost immediately, and we don't fully understand why, using machine learning. And so it lets you just come up with way more sophisticated graphics. I think that's just going to evolve. So it's not just upscaling, which is obviously a piece of it, and filling in the blanks in an intelligent way, but it's literally changing my scene. You can already see people morphing geometry and creating motion and so on activity in the scene, driven by AI rather than so it's elaborate procedural generator to some extent, but where the procedure is so complex you'd never be able to do it any other way. So graphics is now leaning heavily on this very dynamic generation, which is literally the opposite of where it used to be.
Is this happening on a layer above CUDA, or are the graphics work happening in CUDA?
So CUDA is a whole pile of stuff, right? When you think of CUDA, you think of the CUDA C++ language. Excuse me.
And maybe to help, my understanding of CUDA and just to shape where I might be misguided is it's a series of almost like C++ libraries where you're writing in such a way that you have you're able to better leverage the hardware target that it runs on, or that it compiles to.
So it is those things and more. So when I say CUDA, I never mean just the language. I mean this enormous stack of things, from drivers and compilers and languages, yes, but libraries and SDKs, frameworks, anything. Basically anything that gets your program touching the GPU goes through something that is CUDA.
Okay.
Whether it's a PyTorch framework that calls CUDINN, that calls cuBLAST, that calls Cutlass, that calls the compiler, and so many layers away, you'll still get all of those things underneath PyTorch, and even the PyTorch code itself is something that we, NVIDIA, contribute to the PyTorch code base, right? We are massively upstreaming code all the time to add new GPU features, to accelerate PyTorch features. And so CUDA is this entire stack, because nobody writes assembly language, right? That's crazy. And most people don't write C++ low-level code unless they really have to. There's always a library that'll do it for you, or maybe an SDK that's encapsulated. So, use the right tool for the job. And so CUDA is 10 layers of stuff. And at the very bottom layer are the compilers that take the final code and map it onto the GPU threads. Those compilers, the lowest piece of them is shared between the graphics hardware and the compute hardware. But largely, the stacks of software are kind of different, because the graphics software comes very much through DirectX, which is defined by Microsoft. It's a public standard, and so you're working within a generalized framework. there are ways of doing extensions and extra bits which are specific to NVIDIA hardware, but largely speaking, you're within the bounding box that Microsoft describes. And so we've got a whole bunch of compilers underneath that to compile DirectX down to, not directly to CUDA, but to the underlying assembly language. CUDA compiles to assembly, DirectX compiles to assembly, and then the assembler takes it all the way. So the stack is complicated, and all of it is CUDA, at least as a CUDA architect. I have a very maximalist view of CUDA, right? For me, it's very like, because I have to think about all of these pieces. Like when we add something to CUDA, it's like, does this break that compiler? Does it break the framework?
Yeah.
You know, the thing that makes it a platform instead of a bag of bits is that if you are an insane person, you could write a CUDA Fortran kernel and plug it into PyTorch for some reason, and it would work because you'd all agree on memory and program pointers and all the rest. I mean, you'd probably go crazy, but yeah, like and so the fact that it all works together, the whole big picture is what makes it CUDA, and that's largely my job, is thinking about how all these things fit together.
Interesting.
Okay, you mentioned DirectX. That isn't something that I'm familiar with. So I don't know if this is a bit of a tangent, but where you mentioned that you could either go through CUDA kernel or through CUDA to compile to assembly down to the target, or through DirectX. Where do you what causes you to go down the fork of DirectX?
So DirectX is an SDK, an API that Microsoft owns the specification of, which, I mean, it's a set of functions, and it defines how you set up. It's a graphics SDK, I should point out.
For NVIDIA GPUs? Or?
No, for all graphics. So any game that you play on Windows pretty much goes through DirectX.
Oh,
OpenGL is another one. It's a bit older now. Vulkan has taken its place. So if you're going on Linux, Vulkan is owned by the Kronos group. It's also a standard.
I see.
And so there's these different graphics SDKs. They're not completely interchangeable, but functionally speaking, they do many of the same things.
Yeah.
Which, by the way, if you're playing a video game, you will oftentimes see you'll have to upgrade either related libraries, or even in the case of like Vulkan, I notice in my games I can select which one it's compiling down into.
Yeah. And
I just revealed myself as not a gamer.
Yeah. So really, these are in the same way that PyTorch is a framework for writing AI networks and applications. DirectX is kind of a framework for doing graphics and games.
I see.
DirectX is an SDK. Built on top of it is something like Unreal Engine, which is much more of a framework for writing games. Unreal Engine lets you define objects and pathways and all the rest. It's kind of the difference between like an image effect and Photoshop, right? Photoshop's an entire wrapper for like managing computer digital art, and so what something like Unreal is a game engine. It's built specifically for managing all of these different objects and adding scripts to control them and all this other stuff. And on top of it is DirectX, which is or Vulkan, which are the SDKs. Something like Unreal targets both. But they're the SDKs which provide the APIs for interfacing with graphics hardware. So any graphics hardware vendor, so NVIDIA, AMD, Intel, anyone who's making a graphics chip, only has to implement the DirectX APIs and the Vulkan APIs, and every game can talk to them. Now, as with anything, hardware also has specifics to it, and so there are things that work better on an NVIDIA GPU. And so, DirectX is pretty fixed. I'm not a graphics expert, so I don't know how or where we can extend it. Things like Vulkan do have the ability to add extensions, NVIDIA-specific things, just to get at some of the core pieces of hardware there. One of the things we work really hard at on the CUDA side is that because both of these things, the graphics pipeline, if you like, the graphics development pipeline ends up at an assembly, the CUDA generalized software development pipeline ends up at assembly language. We make sure these two things can interoperate. And this is how AI works in graphics. The AI machine learning models and the execution, the inference of them, that's written in CUDA, in CUDA C++ usually. And so you'll have AI kernels, and a kernel is just a program that runs on the GPU, and graphics kernels and shaders which manage special like geometry and other things like that. And they can both coexist and control the machine and call between each other. And so you might have a graphics pipeline calling out into a CUDA piece, sharing the data. And so like an AI could, I don't know if they have AI directly rendering, but it'll return some object structure which then the renderer will then render. So you can call between them. And it's, again, that composition, which is so fundamental to the CUDA platform.
Yeah.
You know, because I'm always thinking, how do these things work together? If I don't want to change CUDA and break graphics, for example, but that allows us to do things like DLSS upscaling, for example, where you can say, okay, well, ray tracing is another example. You call out into ray tracing, it ray traces the scene. You come back to the renderer, which then calls out to DLSS to upscale the shit. And the whole thing is all of these interoperating pieces.
Yeah.
And that runs your game.
Oh, that's crazy. So like when I brought up RTX previously, it was less so for the ray tracing, but the new is it the 5090?
The
5090,
yeah. What's up?
The DLSS 4, or where it can actually generate more than one frame.
Yeah. That's crazy.
Well, that's the future,
Yeah.
right? Like, there's this really interesting thing. I actually think a lot about hardware, partly because, partly because it's just fascinating to me. Like, how do you make a thing with 10 billion transistors that actually work? It blows my mind. But also, the limitations of the hardware and fundamentally the laws of physics affect how we can program this device. Right? So a lot of the performance that you get is gated by how fast you can pull memory out of the memory chips into your compute cores. And that is governed by the fact that the speed of electricity in silicon is about 1/5 the speed of light, and it's got to go this far, and that's like there's a latency built in, right? And the way that you read the memory is you're discharging capacitors, and the 1/RC time constant is set by physics. There's all these bits of physics which govern how fast your machine can go. And so once I kind of that's right. So one of the things that's really important is power, because my laptop has 150 watts. My desktop has 1.5 kilowatts coming out of the wall because America has puny power. But in Europe it's 3 kilowatts, right? I'm English. But even at 3 kilowatts, I've got a finite amount. Even a data center with 20 megawatts coming in the wall only has 20 megawatts coming in the wall. And what that means is that if I double the number of transistors according to Moore's law, which I can totally do, those transistors had better halve in power. Otherwise, I can't use them. If I've a data center with 20 megawatts in the wall, can't upgrade that. And so if I double the power per chip, I have to halve the number of chips. And so effectively, my total performance doesn't go up. Because yes, I've doubled the transistors, but I can only run half of them. So power is the most important thing. And one of the things...
So I have a question. Is this fundamentally why when we talk about, people will talk about how power is going to be a limiting factor for AI and data centers require so much power? I think a lot of people assume like, oh, it's a big piece of machinery and they just equate electricity to like, they're not doing the conversion of watts to bits in their head, but you're essentially suggesting that the reason why a more powerful GPU requires more power is actually that's required to get down to the level where the electrons essentially get converted into information. Is that what you're suggesting?
Yeah, you're spending more power to move the electrons, because you're moving more electrons. And historically, Moore's law, as we shrunk the transistors, it took fewer electrons to turn them on. And that was working great until, that was a thing called Denard scaling largely, which was an observation that as I shrink them by pure luck, half the silicon takes half the electrons, and so my power stayed the same. And that's where you ended up like cranking up these single core CPUs through the 90s. And that ended in about 2006.
Why? With what chip? Was that like the...
So that was the Intel Core 2. That was the moment. So the Pentium 4 started having, they were running at like 4 gigahertz and it was burning power. And it was because what had happened is that as the transistors got too small, quantum leakage current meant the electrons escaped the transistor whether you like it or not. It's nothing to do with resistance, it's pure quantum mechanics. These electrons would just teleport to some other thing. And so you'd lose energy now. And the faster you switch your chip, the faster you would lose energy. So frequency became bad because each time you're moving electrons back and forth, you're more likely to jump out of the transistor and escape.
Is this why there was in like around 2006 or 7, there was a series of CPUs that came out that had like really low frequency? And that was, I remember that was weird because people were saying that it was actually more powerful, but we were thinking of frequency as the power. And so that was like unintuitive. You went from like 4 to like 1 point something, and it was supposedly a more powerful CPU.
So it's a little bit of smoke and mirrors.
Okay.
In that we hit the power wall for a single core. we couldn't shrink the transistors because of this other problem that if I could shrink the transistor to double the power, I can't turn them on, right? And so what happened was you saw frequencies go from 3-ish gigahertz, maybe even 4, boom, straight down to 1.5. And you start to see the Core 2 chip. And the later cores, like, so you end up with 2-core, 4-core, 8-core. I mean, what are we on, like 128 now in one of the AMDs? But, and so the cores started to go up because I had the silicon transistors and I could keep adding them, but I couldn't keep updating the frequency. So one core could not go faster. And it was smoke and mirrors because while the chip nominally had twice as much performance, only if you turned on both cores. But no one's software was multi-threaded.
Yeah.
And if you actually look at the curve of Moore's law, the single thread, the single core performance of a CPU has gone up by a few times, whereas the transistor density has gone up by 20 times. And so unless you're going parallel, since 2006, you're really just not taking advantage of the latest CPUs.
That's mind blowing. This makes total sense. But like, wow. So we've like, from a pure like physics standpoint, we are completely tapped out on what we can do on a single core. And so the only benefit to continuing to make transistors smaller is to parallelize, and parallelization is like a necessity from the software.
Yes.
That's crazy.
In many ways, that's literally sort of the essence of where CUDA came from.
Yeah.
Because in Buck...
and GPUs are all about parallelization.
And it's just massive parallelization,
yeah.
right? The GPU, because it was trying to render pixels, and there's a lot of pixels, and the more threads, the more pixels, you can imagine, right? The GPU, with the CPUs, they said, well, most software is single core, so adding cores is hard. Let's try and speed up the cores as much as we can and only add a few. The GPU went, no way. The future is lots of cores. Let's go big. Like the current GPUs have like 250,000 threads in them.
Oh,
so
shit.
it's just enormous.
Like a Blackwell, like a V100.
Like a Blackwell has like something more than 250,000 threads.
Jesus.
It's completely ridiculous.
That's crazy.
And how do you program these? How do you think about these?
Yeah,
so CUDA is all about how do I take something, it's no longer single thread programming. Like we made decisions very early in the life of CUDA about how do we project the parallelism? Do we hide it? Do we expose it? Do we make the user think about it? And we actually tried to break it into two different pieces where we said, okay, you can think about it in a sort of a coarse granularity or a fine granularity, but you've got to think about it because there's no way you're running 250,000 threads just.
So what did you? I mean, I haven't personally written a CUDA kernel. What's the answer? Like, what decision did you guys make?
So there's two types of parallelism in the world, right? There's the parallelism which they call data parallelism. I've got a large amount of data, like a graphics screen, and I need to render every pixel on the screen, and I can just, the more threads I have, the more I can divide it. It's a divide and conquer kind of story of like just spread it out.
Because each problem is isolated.
Each problem is isolated. We actually call it embarrassingly parallel because there's no problem scaling forever because every pixel does its own thing and it just renders it appropriately. And that's true for a lot of AI type problems, matrix multiply, pretty embarrassingly parallel stuff. And so you can really just throw threads at the problem. And so that data parallel thing is one layer of parallelism. Now the trouble is that you don't only have data parallelism often. You've got other things you're doing in your scene. Using the game example, because we've just been talking about games, you might have multiple objects morphing their geometry, doing procedural textures, fancy lighting, and all sorts of things. And so you're probably not just rendering one object with all of your 250,000 threads. You're rendering 100 objects divided among your... So that's a different kind of division. So you're data parallel across lots of different, what they call task parallel, lots of different tasks. So you break it into separate things I'm doing, but I'm parallel within each one. And a lot of programming models before CUDA said, okay, just think about it in data parallel terms, or just think about it in sort of task parallel terms, like the two forms. And CUDA said, with 250,000 threads, I think at the time we were like 50,000, but it's still a large number of threads. With this many threads, you actually want to be explicit about what you're doing. You want to say, I'm breaking it into these independent pieces, and then within each of these, I'm running 1,000 threads to crank the data on each one. And so we made that breakdown visible, partly because that's also how the GPU runs it. Part of CUDA's job is also to be as close to the hardware as possible so you can get the maximum performance.
Just ergonomic.
And yeah, just the closer you are to the hardware, the more chance you have to optimize for it. And so the hardware inside the GPU has cores which we call SMs, streaming multiprocessors. And I think the current GPU's got 150 of them or something approximately. And it takes those 150 cores and it divides the program amongst them. And each one of these things can run 2,000 threads. So we've got this natural breakdown in the hardware where you split it into 150 independent things. You can gang them all together to work on the same problem if you want, but if your problem has many pieces, like a graphics problem might have, or many algorithms have different sections, you can divide it that way, and then within each one you've got 2,000 threads for cranking through your data. So it's in some ways it's the power of that. This is what allowed CUDA to scale, because as we grew the chip and added SMs, people had already broken their problem into these tasks, and so your problem naturally just gets benefits from having a bigger chip. That's very different from a CPU where the problem was so single-threaded that adding cores, it became hard to take advantage of them.
So I have a question, because I think that humans, we kind of naturally think serially, right? And so when you're presenting this paradigm to people of like, hey, you actually need to break down what you're doing into tasks that can be done essentially at the same time as one another, but still contributing towards the larger end goal. How did you convince people, because it's a fundamentally different way of thinking about programming and problem solving. What was the adoption curve like in terms of convincing people that this was actually a good idea?
Does it feel like teaching someone recursion for the first time?
I mean, they hated it. Weirdly, actually, my background is fluid mechanics. I have no right to be making a programming language. But that was really helpful to me in so much of my career, because I understand where the physicists are coming from. The first goal of CUDA was for the computational science, right? Before AI just exploded. And so CUDA was aiming at weather forecasting and computational biology and those types of things. And physicists are great physicists, but not great programmers. Which is fine, because their job is to know the physics, right? And I totally get that. I was always a better programmer than I was a physicist, which is why I ended up in computing.
I worked in a physics lab in college once. It was like a theoretical physics lab. I remember there was one room and it just said programmer.
It's so widely recognized that if you look at, this is a bit of a sidetrack, but if you look at some of the big research labs, like ULIC in Germany, for example, or the UIUC in Illinois, those are places where they've got their scientists and they've teamed them up with a programmer. So there's someone who knows the science and someone who knows the programming, and together they can do way more than one person. Because the physicist doesn't know how to get the most out of the computer. The computer programmer can write anything if only he knows what to do. And so, by teaming them up, it's been incredibly successful. And so, we're going to these physicists who largely are the programmers of these supercomputers, and we're saying, here is CUDA. You have to think about threads. And they're like, no. And so they hate it. And I get that, because that's not, you're thinking about weather forecasting. You're not thinking about how I map it onto threads.
Well, and I think at the time, it was just like, the problem is gonna be bigger and bigger, but the computing will eventually just solve it. We'll get a computing that's powerful enough that no matter the size of the problem, eventually we'll be able to solve it.
How much did you fight that mentality? Because I feel like that was a lot of perspective of like early software practices. By early, I mean like mid or early 2000s.
So it's always going to get bigger and faster, and that remains true. I can keep adding megawatts to my data center or something like that. But for the physicists, there were things that they wanted to do where you can cross a new frontier. So as an example, 2D weather forecasting doesn't work. You've got to do 3D. But to do 3D, you need obviously way more power than you do in 2D, hundreds of times more and way more memory. And so there's these sort of enabling steps you take where you'll suddenly get to a big enough growth that you can do it. And you don't necessarily want to wait for Moore's law to get your computer big enough. So they're always, PhD students are writing new algorithms for like, okay, I managed to get this hard problem on this small machine. And in many ways, actually, this is one of the fascinating things I see going on in the supercomputing world is, and I shouldn't malign the supercomputing guys too much, but right before the pandemic, I go regularly to the supercomputing conference because there's a lot of my users there and I want to talk to them. And in 2019, it was like everyone was sticking their fingers in their ears and going, la la la, AI doesn't exist. It was like every single talk had a gap where the machine learning stuff should be and no one's mentioning it. And you come back after the pandemic And it's like everyone's like, I put AI into my biology algorithm. But for real, right? Because one of the things that the machine learning algorithms do, again, in that same way that we don't really understand how they do it, we can train them to represent a function that's a complicated function, but it solves it very quickly, very, very simply. And so I've used weather forecasting example. Take that as an example. Weather forecasting, because of the butterfly effect, a small change somewhere on the planet can affect the weather somewhere else on the planet. So you need to do whole planet forecast. Your local forecast takes like the National Weather Service's planet simulation and then does it locally. But you need a big planet-wide simulation. The planet simulation on the biggest computers in the world can do about a 10-kilometer resolution, which is pretty good across the whole planet. But clouds are kind of 1 kilometer, and clouds are pretty important in your weather forecast, right? So we had this problem that the weather forecast was always approximate. There was all these cloud models and these approximation things to try and fill in the gap, but you couldn't get the whole planet at the resolution you needed. And then a few years ago, someone figured out, hey, I can use a machine learning model to fill in the blanks way better than my dumb cloud model can. And there's cloud models, ocean models. It's a very complicated system. But so by filling in these 10-kilometer squares, they could get effectively 1 kilometer resolution. And weirdly, you will have noticed this because you may have noticed in the last few years, the nightly weather forecast on the news has gone from 5 days to 7 or from 7 days to 10. And that's because of AI. That suddenly the weather forecast is, because it gets worse and worse day by day, right? And by having that extra resolution, these machine learning algorithms have allowed us to extend it just those extra few days. And so the reason you get a 10-day weather forecast now is AI. Isn't that weird?
You said the thing that like these ML algorithms would do something that otherwise would be really hard, which is like how did you say it? That they're building.
Well, it's like approximating along a nonlinear equation, right?
Is this kind of where Jensen mentions that like the future isn't code that's compiled to run on a CPU, but like instructions to run on a GPU? He brought that up in the company meeting.
So the AI the machine learning algorithm in general. The AI guys will hate me for this, but the simplistic way of describing it is, imagine you've got a lot of points and you fit a curve through the points, right? It's a polynomial curve fit to points, and instead of the points being in 2 dimensions, it's a million dimensions. And so in AI, in some way, you train it and you get the curve that fits the data best. And then when you do inference, you're basically looking up what's the closest point on my curve. And that's why inference is thousands of times faster than training, because once I've got the curve, it represents my data as well as and it's a curve in a million dimension space. But that's what inference is. And so I can take all this data where an algorithm to figure out what my result is based on all this data would be incredibly expensive. But because I've narrowed it down to this
trend
function effectively, and I can just look up the function, I can take what would be a cloud model with turbulence and fractal goodness knows what, and then I can just say, well, here is the approximation of it that is so good that I'm solving the perfect solution at 1 kilometer resolution in my weather forecast. And this happens not just for weather; it happens for everything, right? This is where computational biology has been revolutionized by AI algorithms doing inference on these incredibly complicated protein models. And all sorts of things, filling in the blanks for translation, all sorts of stuff. These are just high order lookups, effectively. And so all of that means, sorry, that's a long story, but what that means is, I was talking about how power is a problem, right? And power is a problem because as we shrink transistors, we lose more electrons. And so at the end of the day, as we keep doubling our transistors, the power is not doubling in efficiency. And so we're up against this limit where I can't add more transistors, or I could, but I can't turn them on because my laptop's 150 watts or my desktop's 1500 watts. And so if I'm rendering pixels, I can't necessarily go to a 16K screen because the number of pixels I need and the number of transistors I need is more than the physics allows those transistors to render. But these AI algorithms, instead of having they can be 100 times or 1,000 times cheaper to evaluate. So this AI infilling of things like DLSS4, which you mentioned, while it's not the true precise rendering that would have happened, the cost per pixel is in the budget of my laptop where it wouldn't have been before. So even if the graphics chip in my laptop had, sub-nanometer transistors, I simply couldn't turn them on, and I couldn't get the pixels that I'd need. So we'd need, this is really an algorithmics question. We have discovered a new class of algorithms that are cheaper to run with pretty much almost invisibly good different results. And that now opens a new world of things I can do in graphics where I was just maxed out on my transistors before, on my power, before, not on the transistors. So it's this interesting balance of, as we try and get anything, whether it's games or weather forecasting or anything more capable with more data, to simply power the thing that runs them is exponentially hard. And so I need these new algorithms to give me alternative algorithms where I can now fit it in the power budget and still get the good result.
You say, like, in the case of like graphics rendering, you say it's almost invisible, right? What are you is it that the while you can get so much more, the resolution isn't quite what it would be theoretically had the transistors been able to have the power to turn on?
It could be like artifacts of if there's like really fast movement in a game, for example, and it's generating 4 frames ahead, sometimes there's like a slight artifact, right? Because it's not, you're 3 frames ahead now of the actually rendered frame.
Right.
Oh, interesting. I see.
Because it's like in the old days, they used to approximate this and say everything's going to move in a straight line, which is never quite the case in like any complicated movement. That things are following a curve. The AI can actually figure out the curve, if you like. It's looking back in time at previous frames. It's mapping how this thing is moving, but it does assume it's going to continue moving in largely the same way. And when I say assume, it's an AI algorithm. It doesn't make it's a bunch of numbers, but yeah. So it's shockingly good. And you really would need things side by side to see the difference. But given that most things have a largely predictable path, it's just much better at predicting the path than anything we had before.
Yeah.
And so it's not exactly the same as if I'd rendered every image, but it is.
Like directionally accurate.
In fact, it is exactly the same unless something changes direction spontaneously. And those things do happen, and so maybe there would be a glitch.
I see.
I don't actually have a 5090, so I can't run one of these things because
Welcome to the club.
And NVIDIA doesn't. I work at NVIDIA, but I don't get given any of these pieces of
I got a lot
hardware.
of texts today. It came out, and I'm like, I don't.
Yeah, I don't get access to these things. I was at a hackathon last weekend, and like the prize was 5090s.
Oh,
I
shit,
won
I knew
some of this. I won some.
That's so funny.
I think like for those listening, I've actually used this metaphor as well. I think just painting a broader context that the idea of like solving the problem of a pixel, I think is very intuitive to understand, but extend that really to any problem, right? Solving how much red, blue, and green should I be at this frame across many different problems is actually the same type of thinking that people do when you're talking about parallelizing. Is that a good framework to think about how when you're talking about parallelization?
So, in some respects, yes. If you remember, I was talking about data parallelism versus task parallelism, and so solving the color and the illumination and the location all at the same time are 3 different problems, really. And so you can run these things in parallel. So you can solve many things at once. Each one of them might themselves require different threads and data collection to figure out what's going on. And so when you're running some graphics on the chip, then you are dedicating different threads to doing different things. Just because because you have the threads, and second, because you all need to come to the same conclusion at the same time. So you kind of want to be evaluating all these things at the same time. The machine learning algorithms, because they have they're sort of many variable algorithms. They have a very high order of variables they can compute at the same time. You can actually come up with one that solves for all of them at the same time, which is pretty interesting. And it's almost counterintuitive in some way. One of the interesting compromises, I was giving a talk a couple of weeks ago, where about to again a different GPU meetup, and it was I was talking about how if you look at the history of computing, there's been this thing called von Neumann computing that we've used for the last 50 years, as described by John von Neumann, and von Neumann computing is, it's repeatable, it's exact, it's logic, sequences. If you put a certain input in, you get the same input out. And this is largely how all of our computers have worked forever. we are now entering a new age of something we could call neural computing, where it's not exact, right? You put one input in and you might get a slightly different thing out each time because there's too many variables in the problem. It's 95% similar, but it allows, it's error tolerant, whereas von Neumann computing, if there's an error, you crash. With AI, it's actually shockingly tolerant. This is where you get these low precision training things happening, is it's really good at rounding errors. And so they're a completely different class of algorithm. They can do things like solving my weather forecast in a much shorter amount of time. But the result they give is approximate under certain circumstances. Now, a lot of human things are approximate. Translation. There's no fixed answer to the best translation for something, right? There's a lot of nuance. And so humans are very tolerant of this. And so, because our brains work this way. So neural algorithms trade complexity or a very simple solution to highly complex problems in exchange for not having an exact result, but having one that is humanly extremely good. So there's things, maybe I wouldn't have an AI do my taxes yet because I don't want it to hallucinate my taxes. Although that's getting a lot better as well. They're getting, like, if you look at the new AI models, they're getting shockingly good at mathematical problems. Soon I'll just be able to just walk away. And I'm not there yet. But there are certain things where I believe actually in the future von Neumann will be good for some classes of algorithm. Neural will be good for other classes. And then there's future types of computing like quantum computing, which is who knows? I may not live to see it, but at some point, quantum computing will show up, and nobody understands that.
Do you think it'll be like on the graphics chip you mentioned? There's the like the triangle rendering, and then there's the ML piece. Maybe the von Neumann computing versus AI computing, or how did you delineate it? Neural computing. Maybe it'll be something similar, where like the neural computing can leverage von Neumann computing where it's needed.
So, really, the challenge that I see in CUDA right now is to figure out a way to let a programmer control both, right? There is always going to be stuff like networking that is your classical, I'm creating a packet, I have error correction codes, these are not things I want. It doesn't even make sense to try and run a neural network. It's a piece of control software, right? Yeah. And but then I want to connect that to integrate it with these neural algorithms, which are usually running on exotic hardware like tensor cores inside of our chip. So I spend a lot of time in CUDA thinking about how do the tensor cores interoperate with the other parts.
I like exotic hardware.
it's very exotic, like the crazy stuff they do, like ray tracing hardware. Also, another example of things and so the GPU is what we call a heterogeneous system. It's made up of lots of different bits of hardware, specialized at different things. You've got the texture mappers and the rasterizers, which are good for drawing things on the screen. You've got the tensor cores. You've got ray tracers. You've got the very lightweight SM threads for doing bulk parallel stuff. Then you've got you've now got built-in networking things. There's all these other things that are going on inside the chip, and so CUDA's job in some ways is to unify them and present a common platform for being able to interact with them. And so as we build more hardware, it makes it in some ways harder to make a clean, seamless programming model that users will see. And so how these neural algorithms interface with the von Neumann algorithms, and quantum will be coming at some point, I guess, or I'll be retired by then. That question of how to keep it sane, how to be able to control it, and how to be able to like integrate the pieces together. In some ways, the game pipeline is already doing this because it has to render a scene and then pass over to DLSS and maybe have some neural materials and back to more rendering. All of these types of things have to be, it's that orchestration. And so I spend a lot of time, as I said, thinking about how a programmer will be able to control both of these things. Even more tricky is that a lot of the sort of the low-level stuff, certainly the control software stuff, but a lot of the simulation and like weather forecasting stuff, that's done in C++ or even Fortran. All the AI world is doing it in Python. One of the things that we're building very actively right now, and we're releasing a lot of this year, is to make Python a first-class piece of the CUDA platform. What that means is it's not just possible to write a kernel in Python, which you've been able to do for a while. It's that all the pieces in the CUDA platform, the libraries, the SDKs, the compilers, all of it interacts with Python cleanly, so that you can, in the same way you can take a Fortran kernel and inject it into PyTorch if you want, you can take an ML algorithm written as a neural network in Python and drop it into this weather forecast simulation that I've got going on.
Yeah.
I keep hammering on the weather forecasters, but there's actually a lot. And it's that interoperation which has to work so that all of this becomes possible. And that's the platform work that we're doing. We're not yet, even though there's a lot of research on it, at the point of sort of neural hardware. Now we're still at transistors, logic gates, that type of hardware, sort of a classical machine running a neural algorithm. The same is true for quantum mechanics. We're simulating quantum systems on classical machines because we don't have a functional quantum computer yet.
Yeah, I see.
But maybe someone will crack the challenge of what a neural chip
Hardware
looks like. What's something that's not Boolean binary 1 and 0, but like your brain, it's analog, right?
Yeah.
And like who knows what that chip will be capable of? But that's that's a fun research.
When CUDA started, when you joined, you said in 2006.
2008.
2008. What how many? So there's 250,000,000 cores on the latest NVIDIA GPU. How many cores were there then, and like how much? I guess. Well, first I'll start there.
I'm sure you can find a chart of it online somewhere.
Yeah.
So the chip that was out in public was the G80, which I think had, that was just a generation name. I seem to remember it had something like 512 threads per SM and something like 60 SMs or something like that. So the total number would have been about 30,000.
Okay.
30,000, sorry.
Yeah.
30,000. So 30,000 threads is still a lot of threads. The way the hardware runs them is they gang them up into chunks because no one in their right mind is going to run 250,000 separate things.
Yeah.
And so the hardware itself breaks it down into tasks and data parallelism. So there's independent SMs, but each SM is kind of assumed to be working on the same problem. And so it's designed that the threads ideally are all doing largely the same program, just with different pixel data or different weather data or whatever it happens to be. So one of the ways I'm actually writing up a GTC talk for this year. I should mention GTC at some point. I'm writing up.
I guess that's part of the purpose.
I'm writing up a GTC talk because trying to explain how parallelism is different on a CPU from a GPU, because I think it's really important for a programmer to have a mental model of how the hardware is running their code so that they can optimize for it. And what a CPU does, if you think about the parallel SIMD vectorization, something like AVX on an Intel chip, they've got this big parallel vector where you load it up with data and you say, add this and that, or multiply it, or find the biggest or something, and that you give it a big vector, and you've got a single thread of control that just says, apply this across everything. And so what you have is what's called a vector machine, where the parallelism comes from one thread talking to a large vector. The GPU does it differently, what we call SIMT. So that was SIMD, single instruction, multiple data. We have SIMT, which stands for single instruction, multiple thread, where the threads themselves function mostly independently. And so instead of saying one thread has a vector of 1,000 things, what we've got is 1,000 separate threads, each of which load an element. And they load one element of the data and then they work together on that data. So your parallelism is achieved by ganging your threads together, unlike the vector machine where the parallelism achieved by operating uniformly across a vector. What's important for the GPU there is that it means that each thread can, if it wants, do something different. It can do data-dependent operations. You can split half of them and half of them to do different things.
Interesting, yeah.
And that's really important, it turns out, because a lot of problems are sort of somewhat data-dependent. Maybe if I'm calculating a color of a pixel, I care if it's going to saturate and overflow. And so some pixels will overflow and some won't, and I'll do something different. And so the ability to control just that little bit extra, which is what pixels on a screen need, turned out to be incredibly useful for all parallel programming in general.
When we're doing like model optimizations, we're optimizing for faster inference or faster time to first token. Are we essentially ganging the threads in a different way for that use? Am I thinking about that correct?
Yes, that's one of the things you're doing.
But yeah, one of many.
Because one of the challenges of something like machine learning is it's got deep software stack doing many different things, and absolutely, how I map my data onto my threads, how I map my problem onto my hardware, excuse me, is so fundamental to the efficiency and the performance I get. Excuse me. And so it is, in fact, it's so critical to get that mapping between data and threads right, because maybe I use a lot of threads for my data so that I have the maximum parallelism. But it's actually not necessarily the fastest way to do things, because they might all be loading from memory at the same time and my memory becomes a bottleneck. So I might be better off using fewer threads to have less memory intensity. These optimizations are things that Ninja developers have to think about, but more and more you're seeing it move into compilers. And so one of the things you're seeing in the AI space is a lot of JIT compilation, just-in-time compilation, where once you know the parameters of your problem, once you know how big my weights matrix is or whatever it happens to be, once I know that, I can actually optimize my code for that size, because you really want to be getting as close to the peak performance as you can. And so I see a lot of these pipelines, and that's again something we think about in CUDA a lot. CUDA has always offered compiler layers so that people can plug their own languages and things in. Now with these online, runtime, just-in-time compilation flows, what we want to do is we want to give people the opportunity to engage the compiler at lots of different places. We want reduced compile times, because you want, say, here is my inference. The compiler looks at it and says, oh, it's like tall and thin, or it's wide and fat, or something like that. Let's re-optimize the code. That optimization has to be really fast because the user's waiting for their tokens. And so there's these very complicated software flows trying to get the fastest possible inference, and you're trying to balance it. Like if I use the wrong algorithm but I produce it faster, then maybe my time to first inference is still shorter. These are heuristics. There is no perfect answer, because programming is complicated. But yeah, so that mapping turns out to be really critical, and it's really critical to the latency and the efficiency. And then of course there's physics that you can't stop, like I've got to fetch all my data over my wires, and it runs at a certain speed, and so prefetching data becomes important. There's so many variables. It's a fascinating problem of how to tune this.
That's super interesting. I guess we're also running up on time, but something I'm really curious about, like, we were talking about watching gigahertz go down, learning about the cap of gigahertz, and where we kind of started to lose performance as being something around the early 2000s, kind of coincidentally around also when CUDA was being invented. Mm-hmm. Like the foresight for Jensen in the 90s to realize that parallelization was going to be so huge when a lot of CPUs were still very much single core. Like how? Yeah, I guess what did parallelization look like in the early 90s? Do you know, like?
So, I mean, at that time, in the 90s there was, and I wasn't around for that, not at NVIDIA. In the 90s there was this wide competition of different graphics architectures. There were loads of different graphics chip vendors trying out different things. NVIDIA had one set of ideas, which obviously turned out to be a very good set of ideas.
And so these are not GPUs, these are just other types of...
So these were graphics chips. NVIDIA started out in 93 or 3 or whatever it was. Yeah.
It's on our crew next.
Yeah, it's 93. And it started out making a graphics chip just to try and accelerate some of these rendering things. GL existed at that point, I think. And so they were trying to say, how can we render these scenes? And if you've got to produce pixels, one of the ways you can try and do it is, instead of having one thread running really fast doing pixel by pixel, is to have many of them. They weren't threads like we think of as a compute thread these days. These were just, if I'm going to, let's take the rasterizer. The rasterizer takes a triangle, which is skewed on your screen somewhere, and figures out which pixels light up and how much they light up along the boundary, right? So that the rasterizer turns triangles into pixels. That is a very straightforward operation. So if I can make my transistors, my logic gates, if I can gang them up many copies of them, I can render many pixels at once, and my rasterizer goes faster. It's not programmable anyway, it's just the sequence of transistors and logic gates that leads to my pixel showing up or not showing up. And I can just do many of them, and so I can render more pixels per clock cycle. So going wide made sense. in a world where every pixel is different, embarrassingly parallel, as I've mentioned it before, right? And so I think that was the genesis of let's get performance let's get as much performance as we can with dedicated silicon, cloning all of these logic gates to do more pixels at a time, and that grew into, well, let's make them a little bit more programmable and let's end up with this very massively multi-threaded machine. I think an important thing to think about actually is that while the GPU, even in the CUDA sense, is a massively parallel machine, it is good at massively parallel problems. It is not good at serial problems like running Linux. There's been actually multiple efforts to put Linux on the GPU. It's a crazy idea. And you don't put Linux on the GPU because the GPU is no good at it. The GPU's job is parallel computing. It's attached to a CPU. When we think of these machines, we don't think of a GPU as being a standalone device that I would put an operating system on. I'm not attaching a hard drive to it. I mean, I guess I could, but that would be ludicrous. It's more that it is what we call a heterogeneous machine. We think of the machine as a coupling of both of these things. In some ways, my favorite thing that NVIDIA has ever done is the Grace Hopper hardware, where we took the Hopper GPU and we built our ARM-based Grace CPU, server-class CPU, and we connected them together with this really extremely high-speed memory connection between them so they can share data. It makes this unique, it's not just two devices connected by a bus, it's really two devices sharing like cache systems. It's a fascinating device because it's a hybrid device, and you would program it differently from how you program just a CPU or just a GPU. And so in that picture, you would not run two copies of Linux because it's one device. You just run Linux on the CPU where it lives, and the parallel programming stuff on the GPU where it lives.
Why were eGPUs never a hit? And is it just because the bus isn't fast enough to go from like the CPU to the GPU?
Yeah, I don't know. I mean, who really wants an external PCI device?
Yeah.
I mean, I mean, a lot of things don't even have external PCI connectors on the motherboard, so you'd need a special machine. I wouldn't say why weren't they were a hit. I'd say why did they exist at all?
Okay. Yeah.
But maybe that's maligning our marketing department.
Amazing. Okay, we're like 5-10 minutes past.
Should I say something about GTC?
Yeah. Let's.
We can put this at the front.
We'll slice this up. So, great point.
Forgot about that.
Yeah. So this is obviously. I mean, this is. I won't understate it. This is probably one of the most entertaining hours I've had in my career at NVIDIA. And 8 months since we've been here. This has been truly one of the most fun hours. So I really thank you for your time. It was super enlightening. I learned a ton about physics, history, the future, the whole thing. Yeah, I'm a new man walking out of this conversation. But GTC is just around the corner, so we're a month away. For us, it really hits close to home. 8 months ago, we just barely got a booth to attend your guys' GTC.
Seriously?
Yeah.
Wow.
So it's really fun, kind of being on the inside for this come around a year later. But
are you involved this year?
Yeah, we're throwing a hackathon. We're both going to be there.
I'm giving a demo.
Yeah,
It'll be great.
That's awesome.
Yeah, so it's
I think NVIDIA has a booth at its own conference.
Yeah, he's going to be there.
You're gonna be at the booth.
Yeah.
That's amazing.
Yeah.
So we're doing so much on the CUDA side for GTC as well, right? We last year I was looking around and the attendance of GTC has gone through the roof, and I think we had. I shouldn't say that we had more people than the fire limit of the building, because that's probably not okay. But I think we did. It was crowded, but a lot of the conversations that I had was with CTOs and CEOs, which is great. A lot of people have come to learn and understand how does AI fit with the work that I'm doing. But I feel so strongly that it's a developer conference, right? It's like the GPU technology conference. I want to maintain the developer
100%.
feel, and I love that you guys are running a hackathon there. It's like let's have more stuff in there for the engineers. Let's not let the managers take over. And so one of the things we're doing this year is we're curating a whole track of CUDA material, specifically for introductory or advanced level things. We're talking about the huge Python push we're doing and how to program the GPU in Python, how to do it in all the C++ work that's been done. There's just I think we've got 25 or more talks specifically curated about
That's
like for
amazing.
CUDA developers.
So if I end the week and I haven't written my first CUDA kernel, I'm fired.
You're running a hackathon,
Yeah,
man.
So yeah, the hackathon is actually a lot of fun. We're making a 24-hour hackathon in 2 hours, where you
Oh
can
my
only
God.
compete if you're using AI to help you write the code. Otherwise, you won't have the time to write the code fast enough.
I like that.
Yeah. And
You know, I actually had a thought. I give 2 talks at GTC every year. I give the main CUDA talk as one of the CUDA architects. I just talk about where CUDA has come in the last year and where we're headed. And then I just they're nice enough to let me give a personal talk as well. And I had this thought, and I'll probably never be allowed to give another talk again if I do this. Where,
we won't post this till after.
where I'll get AI to write the talk, and I'll get AI to render all the images,
Oh, nice.
and I'm not going to read it.
You'll do it live.
And I'll stand up and I'll just say it like I mean it. And that would be amazing.
I love it.
How good could that be? And then I'll never be allowed to speak again. So maybe I won't do that.
I hope there's like 2 really good hallucinations. Not enough that people really notice, but yeah.
I'll be like, what? Maybe I should make like a backup talk.
That's amazing. Well, yeah, this is super exciting. What we'll do is put a link to where you can get a ticket.
If it's not sold out already,
yeah.
it's getting close.
But yeah, this is super exciting. I'm excited to see both your talks. And yeah.
Yeah, thank you. And you know, you can attend online as well as attending in person is better because you've got all the other developers around you.
Yeah.
And you can attend hackathons and all sorts of cool stuff. But it's also all the GTC stuff, which I love, is streamable online afterwards, right?
Amazing. Yeah.
I use GTC as a massive archive. When people say, hey, how do I do this? I'm like, here's a talk you should watch.
Yeah.
Because all of the ninjas, the people, far better programmers than I've ever been at NVIDIA, who really understand like decompression algorithms and parallel, like crazy stuff like that, you can hear them talk.
Yeah.
And it's all recorded as well. You can watch what like all of these techniques that they can tell you about.
That's
It's
amazing.
just fascinating.
Yeah.
I think from beginner to advanced, and you know, we're curating it especially this year, but there's this archive going back years, and you know, it's the best educational archive we have for GPUs.
That's amazing. Hell yeah. So
All right.
in short, physics is holding us back. Get your ticket to GTC, and if you get a 5090, let us know.
I want one.
Yeah.